You ever wonder what actually happens when a new feature, just appears in your favorite app? It's not magic, that's for sure. It is a super complex, automated journey through this whole world of cloud-native architecture. So today, we're going to demystify all of it. We're going to follow one single new feature from just an idea on a developer's laptop all the way to your screen. And where does this journey begin? Well, it starts with a really fundamental shift in how we think about building software.
To really get the new way, you've got to look at the old way first. Imagine your entire application is just one giant block of code, a monolith. A single bug in some tiny, forgotten corner could bring the whole thing crashing down. Seriously. Pushing out even the smallest change was this high-stakes, hold-your-breath, all-or-nothing event. The new way? Well, it smashes that massive block into tons of tiny, independent pieces called microservices, and that makes everything way more flexible and way more resilient.
So, our features journey kicks off with this one crucial decision. Instead of adding another brick to that giant, risky wall, we're going to build it as its own, independent thing.
At its heart, the concept is actually pretty simple. Instead of one big app, you have dozens of tiny little ones. Each one does one specific job, like one handles user profiles, another one processes payments. The key, right, is that they all work together, but they can be updated or fixed or even replaced completely on their own without messing with anything else.
Now here's the lingo you're going to hear out in the wild. When you hear engineers talking about decoupling a monolithic application, this is exactly what they mean. It's just the fancy way of saying they're creating freedom and speed by carefully breaking things apart.
Okay, so we've got our new feature, it's built as a microservice, awesome. But now we have a new problem. How do we package this little piece of code so it can run absolutely anywhere? And with potentially hundreds of these little pieces all flying around, who's going to manage them all?
The answer to that packaging problem is containerization. And honestly, the best way to think about it is like a standardized shipping container. You pack your code and everything, and I mean everything, it needs to run inside this box. Now it doesn't matter if you're sending it to a developer's laptop or a massive data center, it's going to work exactly the same way every single time. This is what finally kills that classic developer excuse of, but it worked on my machine.
So that brings us to the manager, and there is just no better way to think about this next tool than with this powerful phrase right here. If containers are the individual applications, this next thing, this is what tells them all what to do, but on a massive scale.
And that tool is Kubernetes. Look, if you have 10 containers, you could probably manage them by hand. Maybe, but what if you have 10,000? Yeah, no way. Kubernetes is the orchestration platform that automates everything. It tells containers where to run, how many copies to make, and it replaces them automatically if they crash. It is, quite literally, the brain of the entire operation.
This brings up a really key distinction in how all these services can communicate. On one hand, you have orchestration, which is what Kubernetes does. It's like a conductor, telling every single musician exactly what to play and when. But then there's also choreography. This is where services just react to each other's signals, kind of like a troupe of dancers who all know the steps without needing a leader in the front. Modern systems actually use a mix of both.
So, our feature is built. It's packaged up nicely in a container, but how does it actually get from that developer's laptop to the millions of people using the app? Well, for that, you need a fully automated assembly line just for code. And this assembly line is called CI/CD. It stands for Continuous Integration and Continuous Deployment. Its entire job is to create a pipeline that automatically grabs new code, builds it, runs a whole battery of tests on it, and then, if everything looks good, it pushes it out to the world, all without a human ever having to touch a button.
Let's just walk through this pipeline really quick. It all kicks off the second a developer commits new code. That single action starts the whole automated process. This idea is called GitOps, where the code repository itself becomes the master blueprint, the single source of truth for what should be running live. The pipeline then builds and tests the code, and finally deploys it safely using a really cool technique like blue/green, where the new version runs right alongside the old one until we're 100% sure it's safe to switch all the traffic over.
And there it is. Our new feature is now live. But the work isn't over. Not even close. In a lot of ways, it's really just beginning. Now we have to manage it, secure it, and make sure it can handle the chaos of real-world traffic. So 3 key tools handle all this. First, you've got the API gateway. Think of it like the main entrance or the bouncer at the club. It manages security and directs all incoming requests.
Then, load balancing steps in to distribute all that traffic, making sure no single microservice gets totally overwhelmed. And finally, a service mesh handles the really tricky part, all the complex, messy communication between the microservices themselves. It's like a dedicated, super intelligent network layer just for your services, handling security, retries, and all that stuff, so the services don't have to worry about it.
So what happens when traffic suddenly spikes? In the old world, you might try something called vertical scaling. Making your one server bigger and more powerful. But the cloud-native way prefers horizontal scaling. Instead of a bigger server, you just add more servers. And this is so much better for fault tolerance, because if one server fails, the others just pick up the slack. No big deal.
With all these moving parts, just knowing if a service is up or down, that's not nearly enough. We need observability. This means we're collecting super detailed logs, metrics, and these things called traces that literally follow a single request as it bounces between all the different services. It's the difference between knowing a patient has a fever and having the full diagnostic chart that tells you exactly why they have a fever.
And that brings us to the final and maybe the most important part of this whole journey. All of these tools, all of these techniques, they're all in service of a single philosophy: building systems that are designed from the absolute ground up to be resilient and to heal themselves.
A core part of this philosophy is something called immutable infrastructure, and it's a radical idea. You never, ever log into a live server to fix or update it. Why? Because that leads to configuration drift, these tiny, undocumented changes that are impossible to track, and they always cause errors later. Instead, you treat your servers like cattle, not pets. They're disposable. For any update, you destroy the old ones and you just replace them with brand new ones built from a perfect template.
Okay, so how do you get confident that your self-healing automated system actually works? Well, you adopt this seemingly insane philosophy. You try to break it, intentionally, in production.
This is chaos engineering. It's a practice pioneered by companies like Netflix for one very simple reason. They needed to make sure their streaming service stayed online even if their cloud provider had a massive outage. So teams will intentionally inject failures. They'll shut down a server, they'll introduce network delays, all to see if the system responds the way they expect it to. It's basically a fire drill for your application. And one of the key safety mechanisms that chaos engineering is designed to test is the circuit breaker. If one microservice starts failing, this pattern automatically detects it and temporarily just stops sending it traffic. This gives it time to recover. And its real power? It prevents a small, localized failure from cascading into a total system meltdown. It contains the blast.
So, from breaking down that monolith into microservices, to packaging them in containers, orchestrating them with Kubernetes, delivering them through CI/CD, and running them with this mindset of resilience, you can see this is so much more than just a collection of buzzwords. It is a complete philosophical shift in how we build and operate software today.
So we've gone on this whole journey, from a simple idea to a live feature that's running on a system designed from its very core to expect and survive failure. This isn't just about making apps more stable. It's about building a foundation that's fundamentally more resilient. And that leaves us with a truly fascinating question to think about. When our infrastructure can literally heal itself, what are the new limits of what we can dare to build on top of it?